anytime something falls near the surface of the Earth, it falls with constant acceleration. And you probably had a chance to measure this. Okay. Now, that last bit, in the absence of air resistance, is kind of important. Here in high school physics land, and actually in your first year of college physics land, we disregard air resistance. We ignore it. We act as though it's not real. It is real. If we actually computed air resistance, things would get dramatically more complicated really fast. So typically in physics, we ignore it. There are a couple problems where we specifically think about air resistance or wind resistance, but for the most part, we just pretend it doesn't exist, which is a lie, and leads me to one of my favorite jokes. I know I have lots of future engineers in here. I don't think I have any future math majors. I don't know that I have any future physicists. I've only seen one future physicist in about 10 years. Physicists assume that, back it up. Engineers assume that the equation is an approximation of the real world. Physicists assume that the real world is an approximation of the equation. Mathematicians have yet to figure that there is a connection. Anyway, so here in physics world, we pretend air resistance doesn't exist. Free fall acceleration is shown as g, lowercase letter g. So we talk about lowercase letter g it's an acceleration. It is not a force. So this is not g force. This is an acceleration. And g is equal to 9.81 meters per second squared. That's the magnitude of g. Your book does something kind of strange. So all of those equations that we've used that have acceleration in them. And if you haven't figured it out yet, what we're doing today is we're flipping everything 90 degrees. So we're still going to talk about motion only in one direction, but we're now going to talk about it on a 90-degree angle from where we had been talking about it. And this shouldn't be hard, but every year it just throws a monkey wrench into the works. The way your book handles that is it swaps out g for all the a's in those equations, and it makes g a positive value. It uses the magnitude, and then you have to put in negative g. I personally find it a whole lot harder to deal with. I've tried it both ways. So what we'll continue to do is just leave that a in there and know that if the acceleration is due to gravity, we show it as negative 9.81, and that should be meters per second squared. I don't know what happened to the slide. We use sine as a proxy for direction. And so if this is the surface of the Earth, as long as something is traveling down towards the surface of the Earth, because we're still using our old conventions of the Cartesian coordinate system, where this is positive and this is negative and this is positive and this is negative, down towards the center of the Earth, that motion is negative. So its velocity is negative. Its acceleration, if it's accelerating towards the surface of the Earth, towards the center of the Earth, is negative. If we throw something up, its velocity is positive. Okay? So up away from the Earth is positive. Down towards the center of the Earth is negative. Well, that's great. Now, here's the question I want to ask you. Whoops. Everything that goes up does what?
Must come down.
Must come down. You've known that since you were little kids. Kids at about a year start experimenting. We call it the gravity game. Hey, look, gravity works. If I hold this out, it drops. Oh, that too. Woo! Don't give them anything fragile. If the only force acting on something is gravity, which means it's in free fall, Its acceleration is negative 9.81 meters per second squared. Period, end of sentence, end of story. If nothing else is acting on it, its acceleration is straight down towards the center of the Earth at negative 9.81 meters per second squared. You're going to know that number backwards and forwards and inside out. If we toss an object up into the air, as you all did recently, as that ball is traveling upward, what is its acceleration? Its velocity is positive. What's its acceleration? Negative 9.81 meters per second squared. When it comes to the very top of the flight and it stops for a moment and it hangs there for a picosecond before it starts to fall back down, at that moment when it stops and hangs in space, what's its acceleration in that one moment? Negative 9.81 meters per second squared. As it starts to fall back towards the Earth and you have to run to avoid being bonked on the head, what's its acceleration? Negative 9.81 meters per second squared. Are you getting to feel like there's only one answer here? Yeah. Any object that is only being acted upon by gravity is accelerating at negative 9.81 meters per second squared. That is 9.81 meters per second squared towards the center of the Earth. Every second, it's going almost 10 meters per second faster. So let's think about, because I see troubled faces on one particular point. So let's look at a little ball being thrown upwards. And it reaches that top of flight and it stops for a moment. And then it continues to fall towards the Earth. So there are two things to think about with that motion. And one of them is velocity. I mean, actually, there are, what, four things. There's initial velocity and final velocity and acceleration and time and displacement. We've got all that stuff. Yeah, whatever. But let's right now talk about the velocity and the acceleration. So on this side, its velocity, its initial velocity as you throw it upward, and its velocity as it's traveling upward. What is the sign of its velocity? Positive. It is moving in what we would, by convention, we call a positive direction. That is away from the surface of the Earth. So velocity here is positive. What about its acceleration? What's its acceleration as it travels upward? Negative 9.81 meters per second squared. Negative 9.81 meters per second squared. What is happening to the magnet? What's happening to its speed? It's slowing down because it has a positive velocity and a negative acceleration. This is just like you driving in what we decide is a positive direction and hitting the brakes. You have a negative acceleration. Your acceleration is backwards of the way you're traveling, and you have a positive velocity. You are slowing down. Now, once that ball reaches the top of flight and it for a moment has zero velocity, is it still changing its velocity in that moment? Yes. It's going from a positive velocity to a negative velocity, and in that very moment where, let me see if I can move this around a little bit, where for one single little second velocity is equal to 0, it still has a negative acceleration. And that negative acceleration is negative 9.81 meters per second squared. Okay, we got it, Moser. And then as that ball starts its downward travel, what's its velocity? Well, we don't know the magnitude of its velocity, but is it positive or negative? It's negative, because it's now moving in a negative direction. And what's its acceleration? Negative 9.81 meters per second squared. And what is happening to the magnitude of its velocity? What's happening to its speed? Speeding up. because now it's moving in a negative direction with negative velocity. This thing is speeding up. It's getting faster and faster. That makes sense? Okay. I'm glad you say that. So, this crazy person, they're not bungee jumping, they're skydiving, but they've jumped out of an airplane. They are accelerating at negative 9.81 meters per second squared. This ball, which is currently in the process of being thrown upward, is accelerating at negative 9.81 meters per second squared. These turkey poults, if they jumped off the top of their water bucket, they're baby turkeys, would accelerate at negative 9.81 meters per second squared. Anything that is being acted on only by gravity is accelerating at negative 9.81 meters per second squared. Yes?
This is because
Gravity is constant. Force of gravity does not change at any point on Earth. There are incredibly minor, like imperceptible differences in the amount of force that gravity can exert on you based on how far away you are from the center of the Earth. So like in the bottom of Death Valley versus the top of Mount Everest, you would still not notice it. If you fall off the top of Mount Everest, you're still going to accelerate downward at negative 9.81 meters per second squared, and it's going to hurt. It is imperceptibly smaller there because you're further away, there's less force being exerted on you, but it's so tiny that we can say, just like we can say, there's really no air resistance. We can say, nope, any place on the planet, any place within the atmosphere of the Earth, as long as you are within the atmosphere, acceleration due to gravity is negative 9.81 meters per second squared. Once you get outside the atmosphere, it changes because you're outside sort of the principal gravitational field of the Earth. And so there, it's different. But yeah, top of Mount Everest, bottom of the Dead Sea, bottom of Death Valley, the deepest pit you can dig, you're still accelerating at negative 9.81 meters per second squared. That gravitational force that causes that acceleration is equal in all directions from the Earth and, every place on the Earth. Different once we get off the Earth, but we're not there yet. Okay, so here is the part that we talked about a little bit, but I'm going to hit. It's important enough that I'm hitting this a second time. These are the kinds of problems where screwing up. So in the other problems, if you screwed up the sign, it was just like, oh yeah, well they're going south, not north. Okay, I get it. On problems on the y-axis, which is where we have just gone, we've just gone from the x to the y. If you screw up the sign, you get a different magnitude. Because suddenly you're adding two things when you should be subtracting them. So you have to pay super, super careful attention to sign in these kinds of problems. Anything traveling up has a positive velocity. It's got a positive displacement. Time, of course, is always positive because it just marches forward whether we care for it or not. Anything traveling downward has a negative displacement, has a negative velocity. Of course, you all remember already that the acceleration is always, 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 always negative. Negative 9.81 meters per second squared, yes. You will, by the end of this year, you will wake up and be able to recite that in your sleep at 2 in the morning with no coffee when if I came into your house and shook you awake. Okay, which I mostly promise not to do. G is always given as a negative. This, of course, should be a lowercase g. I think I got auto-corrected there. Negative 9.81 meters per second squared. The acceleration is always towards the center of the Earth, whether the motion is or not. When you fall, if you walk out into this hallway and you trip over your own feet and you fall and you hit the floor, you were accelerating not towards the floor. You're accelerating towards the center of the earth, which I think for somebody who falls down as much as I do, I think that this lends a whole different kind of importance to falling. Like, no, it's not that I'm a klutz. It's that the center of the earth finds me very attractive. And every now and then, that attraction is overwhelming. Boom! Now, the floor gets in the way of our relationship, but, really, it's the center of the earth attracting you. So that acceleration is always towards the center of the earth. Therefore, that acceleration is always negative. We're going to do the problem on page 64 together. I already put the new problems on the board. We've got 5 from the book, from the page 64, and 3 from the chapter review. So let's go ahead and do, well, here, I'll put up my last slide because, hey, physics is fun.
This makes me so happy.
I'm so glad. We're going to do this one together. We're going to do the sample problem together, and then, or the practice problem. No, sample problem, and then you'll do the practice problems, and I'll walk around and spy on you. So we're starting off with Jason hits a volleyball, and this is on page 63 in your book. Jason hits a volleyball so that it moves with an initial velocity of 6 meters per second straight up. Notice that 6 meters per second is given as a positive. This is the point where you may want to. So Jason hits a volleyball so it moves with an initial velocity of 6 meters per second straight up. If the volleyball starts from 2 meters above the floor, how long will it be in the air before it strikes the floor? Assume that nobody else touches the ball after Jason does. This is where drawing the picture starts to become really essential, because you're imposing these events on an axis. So I'm going to draw the ball, and I'm going to draw the floor. The floor is, in essence, our x-axis. The floor is our 0 mark on the y. So this is 2 meters. It's starting 2 meters up. It's going to travel some distance upward, we don't know how far, and it's going to hit the floor again. We know that it has a VI of 6.0 meters per second. We know that it has an acceleration. What is the acceleration on this ball over the entire course of its flight? Negative 9.81 meters per second squared. They mumble like a bunch of zombies who have been programmed to say negative 9.81 meters per second squared in place of brains. Perfect. What is the displacement of this ball? Negative 2 meters. Now, here are the 2 pieces to be careful about. So, okay, number 1, I see a few crinkled brows. Why is it negative 2 meters? Because it starts here and it ends here. Remember that displacement is not the distance it travels. Displacement is how far it ends up from where it started. So it ends up 2 meters below where it started. Now here's the other thing. What have we been referencing displacement with? Delta x. Well, guess what? Displacement is no longer delta x. It's delta y. Well, you know what? And I have every single year I have a couple students who go, "Can't I just call it delta x? Can I please just call it delta x?" No! Why not? Because next chapter we're going to have delta x and delta y. It's okay. You'll be fine. Nobody has died of physics in this room yet.
Not in this room.
Oh, well, there's that technicality. Well, whatever. You'll all be fine. I promise. I have to end the year with the same number of students I start with. I can't lose anybody after chapter 2. Okay, so our delta y, our displacement is negative 2.0 meters. And we are looking for what? Time. We're looking for delta t. So all we have to look at is what equation we have that ties those 4 things together. So note cards out. The resume recording, sorry. Okay, so the most straightforward, most obvious thing to do is to use, delta y equals vi delta t plus 1/2 a delta t squared, except that requires a quadratic solve. And your book takes a second route, which is to ignore this equation. So we'll pop this out of here. And instead, to look for VF, because they're going to use VF equals VI plus A delta T. Solve this for delta T. But in order to do that, we have to have a value for VF. Okay. So we're going to kind of set this up there. So now, let's see what we can do with VF, having VI, A, delta Y, and VF. What can we use that connects those four? How about VF squared equals VI squared,
Plus
2A delta Y in this case. Yes, plus 2 acceleration times displacement. Okay, so that means that VF is equal to the square root of VI squared plus 2A delta Y. Well, at that point, this is not such a terrible substitution. We have an expression for VF in terms of the other things that we do have. So I'm going to get rid of that. So now, what we can do, let me shrink this. So what we can do at this point is take this equation, VF minus VI over A equals delta T, and plug that in for VF. Okay, so we have the square root VI squared plus 2A delta Y, that quantity, and I'm going to make sure it's really, really clear to me as well as to other people where that radical sign stops, minus VI, all divided by A, is going to give us delta T. Okay, so I'm going to take this to the next page. Whoops. And we're ready to start plugging in values. So our VI was 6.0 meters per second. That quantity is squared, plus 2 times, what's our acceleration? Negative 9.81 meters per second squared. And what's our displacement? Negative 2. Why is that so important? Well, what would happen if that wasn't negative? We'd have the square root of a negative number. This is, once we're into free fall and everything's on a 90-degree flip, those negative signs, we very often get a point where, like, I've got a negative under a radical. So, okay, that whole thing minus 6.0 meters per second squared, all divided by negative 9.81 meters per second squared. Whoops, that's not squared. Okay, now a couple things I want to remind you of. Whenever you take the square root of something, your answer is given as what? Plus or minus this magnitude. So you have to think in your own head, this was VF. Is that going to be a positive or a negative? It's going to be a negative because that ball is accelerating downwards towards the surface of the Earth. So you have to remember that for yourself, that final velocity is going to be a negative number. Okay, so start calculating. What's your raw answer? Raw.
1.495830.721 seconds.
Okay. Yeah, and I think yep, that's exactly what I got. All right. Now, how many sig figs can we have? Yes, 2. So we get a time of 1.5 seconds. Now, if you were, and a lot of you do this, and it's a good habit to be in, doing sort of breakdowns as you solve, you can pop in numbers. So the final velocity was negative 8.674099, etc., minus 6. So it gives you a negative 14 something. And really that's the only one that you sort of do a breakdown to solve. And this was divided by negative 9.81 meters per second. If you forgot to make this final velocity negative, you get a radically different answer. Because then you're taking 8 minus 6 rather than negative 8 minus 6. So you really, really have to pay super close attention to sign in these because it will change the magnitude of your problem, of your answer. Okay. Page 64, numbers 1 through 5 are assigned. Actually, you know what? I'm going to ask you to do something. So on page 64, numbers 1 through 5 are assigned, but I want you to save number 1 for last. Don't do number 1 first. I wish they didn't have it in there first. It puts your head on the wrong track. So, start off with, I'll tell you what, I'll just not assign number 1. Just skip number 1. You just finished it, didn't you? I'm sorry. Skip number 1. I don't like it. I think it messes up your head. So make that 2 through 5 and then the chapter review problems. I will have the worksheet for 2F tomorrow. So I'll give you that tomorrow and we'll spend some time on it. And we'll probably have a FIP quiz in here on Wednesday. So, okay, that's it, folks.